So thank you for turning up. I know it's 6 o'clock, I know it's late. It's only a brief talk, so I won't keep you for too long. The title of my talk is HPC and Scheduling for Real-Time Systems. My name is Mark Davey, and I work for the Foundry. For those of you that don't know, the Foundry was founded in 1996. It develops award-winning visual effects, computer graphics, and design software, and is used throughout the world by artists and designers. The high-performance computing group within the Foundry has a very simple remit, and that remit is please make things go faster. That's basically what we try to do. We try to take the software that we already have at the Foundry, and we try and make that go faster, and we develop frameworks, and I'll be telling you quite a bit about those frameworks in order to help facilitate speed and efficiency on computers. So what exactly will I be talking about today? Well, the HPC group has been developing a number of technologies aimed at real-time compositing and rendering. What we're trying to do is to take the post-production effects that currently are used in things like Nuke and speed them up to the point where they can be used in real or interactive time. And that means that those effects, which currently aren't real-time, currently only used in post-production, can get moved along or earlier on in the pipeline, so may be used during production itself, on set or near set. And so today in particular, I'm going to be talking about three things. The first is Blink, which is a write-once, deploy-anywhere image processing framework that's been developed at the Foundry. I'll also talk about the authoring of Blink-based effect graphs in Nuke. I'm sure that you all know what Nuke is. It's our compositing software. And I'll be explaining how we're exporting these graphs to use in a suite of applications that we've been writing, which are more suited to real-time execution. And thirdly and lastly, I'll be talking about how we manage to schedule those graphs in our suite of applications to make the use of all of the available compute devices on those systems in order to maximize performance. But let's start at the beginning. Why was Blink invented at the Foundry? Well, Blink is a 2D image processing library in its essence, and there's a lot of 2D image processing that goes on at the Foundry. It's used in standard effects like grading, keying, noise reduction, etc. And so it's very important for us to try to make those kinds of algorithms run as fast as possible. The Foundry, as I said, was founded in 1996, and we have a huge amount of legacy code, most of which was run or designed to run on the CPU. But as we all know, GPUs are in the ascendant, and they are now very good at image processing. And a lot of our customers, such as artists, they have very powerful GPUs, but not all of our customers do. So for instance, if the effects that are being run in Nuke are to be run on a render farm, then a lot of render farms don't have GPUs. And so we still need to maintain a CPU fallback for all of our algorithms. But what we don't want to do is to have multiple code bases, one for the GPU, one for the CPU, maybe multiple for the GPU because there's a variety of languages. Obviously, that gives rise to all sorts of debugging, maintenance problems. When new hardware comes out, the code that we have might not be fit for that new hardware. So what's the solution? Well, as I said earlier, the solution is a framework called Blink. Image processing algorithms are expressed as kernels, and these kernels are written in the C++-like language. And very importantly, the kernels themselves contain a number of pieces of metadata which allow us to optimize the performance of these algorithms on a number of devices. This metadata includes things like data access patterns, which I'll speak a bit more about later, image formats, image boundary conditions, etc. A really cool feature of Blink is that it gives us JIT compilation. That means that we can compile and execute the algorithms at runtime. It's not a compilation procedure. Now, the execution of the kernels is handled by the framework, and that's very important. We don't want the users of the framework to have to worry too much about the execution of those algorithms. We want them to spend most of their time just thinking about the algorithms. We want them to leave all of that stuff to us. Blink gives a lot of profiling information, which I'll come on to later. It's very important. Things like memory allocation, execution, and transfer times. something that's highly unusual, I've found, is that our framework is able to give us numerically identical results across all supported devices. So for finite floating point numbers, all of the results are bitwise identical. And that, again, is very important when you're thinking about using multiple devices to do your processing, because you don't want to have seams or different results depending on where you run your algorithms. Now, these kernels, written in the Blink language, are automatically, or can be automatically translated to a number of different backends. At the current time, those backends include CUDA, OpenCL, GLSL, and x86 for the CPU. And you'll see a little asterisk there pointing to the fact that we do a very good job of creating or translating code for the CPU using a whole range of SIMD instruction sets from SSE2 all the way up to AVX2. So how at the moment is Blink used at the Foundry? Well, there's two key areas where it's used, Nuke, and in a variety of collaborative projects. Within Nuke, it's used in two quite different ways. Firstly, we have either ported or developed a whole suite of plugins that now provide GPU acceleration, including things like Ocular, which is our stereoscopic tool set, denoising, depth defocus, retime, convolve, that sort of thing. And then more relevant perhaps to this talk, we have a special Blink script node. And the Blink script node allows within Nuke itself for people to code their own algorithms, their own effects within Nuke, have them translated, have them run on the GPU so that people can get the full experience of GPU acceleration without having to have any other tools. And on certain hardware configurations, the Blink script can make use of multiple GPUs if they exist. Here at FMX, we're demonstrating some of the technology that I'm going to be describing a bit later in one of our collaborative projects called Dream Space. So please, if you get a chance, come down and see us in Tower A, and we'll give you demonstrations or fill you in on any more details that I don't cover today. There's a further project at the Foundry that we're working collaboratively with other companies called ASAP. We're working on scalable renderers, and that, again, uses a lot of the technology that I'll be describing. So with Blink, in Nuke, you can, by using Blink scripts, you can come up with sophisticated and complex compositions. You'll see on the right of the screen perhaps a simple graph of operations that's designed for keying. So you'd have a green screen image, some map that you want to put at the back, and I've just got some credits here or some copyright information. The keying's done, filtering's done, images are merged together, lens distortion, etc. And I'll be using this graph later just to highlight some of the results that we've been getting when we try to move into real-time performance. Okay, so when we use Nuke within, when we use Blink within Nuke, we get a great ability to author our compositions, our graphs, but we don't get real-time performance. And that's for a number of reasons. Firstly, Nuke is a scanline renderer. It's designed to handle massive graphs containing extremely large images. And scanline renders, scanlines themselves are not optimal for GPU processing. Nuke doesn't provide, for instance, live support, live input, and that's very necessary for a lot of the projects that we're working on. And importantly, Nuke isn't able to harness all of the compute devices in parallel. You can't say, run some of my effects on the CPU while at the same time running some of my effects on the GPU. So it was decided that in order to get more real-time performance, we would have to move Blink outside of Nuke. And this moving out of Nuke starts really with exporting the Blink graph effects out of Nuke and saving them to disk. These files contain the graph topology and all of the Blink code within all of the nodes, within all of the kernels. And what we've done is we've developed a whole suite of applications that can read in those graphs, read in those kernels. At runtime, it can recompile them and rerun them. These applications allow us to composite our 2D graphs with live and 3D content. And it gives us the possibility of using all of the compute devices for running our effect graphs. This last point is very important. In order to get real-time performance, we really do need to make use of all of the resources available, not just the CPU or the CPU, but perhaps multiple GPUs, as well as the CPU at the same time. So that brings me on to heterogeneous compute, which is the fancy way of saying running your software on lots of different devices. As I've said, Blink makes it possible to run effects on any of the supported devices, giving you identical results. But what we want to do is to run our effects on all of the devices. And so we need a framework for scheduling across devices. Now, this is a very complex problem because there are lots of ways of breaking that graph down into different ways of breaking it down and deploying different parts of it to different devices. Talking about breaking things down into little bits and deploying them on different devices, the way that I tend to talk about that is we need to exploit parallelism in the graph. And there's two different kinds of parallelism that we might harness. First is task parallelism. Basically, if we have tasks with no input dependencies, then we can run them in parallel on different devices. The second is within a particular node within the graph, we can break up the input data into lots of little pieces, send the bits of that input data to different devices, have the processing done in parallel within a single node. And in both cases, whether we're harnessing task parallelism or data parallelism, we really have to consider the fact that sometimes, well, relatively speaking, it can take a long time to send the data to and from devices. So when you're trying to schedule, when you're trying to work out the best place to do your processing, you really have to take into account how long it's going to take to get the data there. It can be quite a substantial amount of your time. And finally, for this slide, we focus in the main at the moment on data parallelism. So what we're trying to do is break images, break input data into little pieces, and deploy those to different devices and have the work done in parallel that way. The next few slides just give you a bit of a background on what I mean by breaking pictures up, deploying them on different devices, and having them processed. Here's a very simple example of a process that you might think of doing on an image. The image on the left, I want to invert it. So what I could do is break that image up into a number of pieces. Here I've broken it up into 2 pieces. The pieces aren't the same size. I've transferred those pieces to different devices, and I've done the processing, resulting in an inverted image, which, by the way, is now split up over a number of devices. Now, because every output pixel only requires one input pixel, this is called point access. And so a question obviously comes to mind. What fraction of the image should be sent to each device? I'll leave that as an open question for now, but obviously that's something that you have to consider. How much do I put on the GPU? How much do I leave on the CPU? You're going to kind of have to worry about the compute capabilities of the devices, and I'll come on to that in a bit. A slightly more complicated example of breaking up the data and sending it to different devices is a blur. Here I'm going to try to blur this initial image on the left. I'm going to send pieces of data to the different devices, but note the little green areas. These little green areas are called aprons, and here, in order to produce the output, each output pixel requires a ranged access of pixels around it in order to do the blur. And so we need to send those extra pixels over to the device as well. And so if you look in those green areas, you'll see that there's a kind of duplication now of data. The sort of the line of the F, the middle line, if you like, of the F is now on both devices. So we've had to send more data overall in order to do this breaking up. Now, obviously, because we have managed to blur that image, but the results are split across devices. And so you really need to think about what the next node is in the graph, because the next node on the graph might require all of the image to be on a specific device. And if it does, then this data is then going to need to be transferred somewhere else. So you kind of get the feeling that this is a complicated problem to work out, certainly manually. Certainly if you had a graph, to try and figure out how you do it is not trivial. Just one final example here. This is a distort kernel, and this basically means that any output pixel could take any of the input pixels. And so the whole image has to get sent to each device because it may be required in order to do the effect. And this is called random access. So on now to the meat of the scheduling problem. How do we decide the data partition for all effects in a graph? And basically, we need to take 3 things into account. We need to understand the data access patterns, as I was just going on about, for each effect. We need to understand the compute capability of each device for each effect. And we need to understand the data transfer costs between all devices. And as you can see, this results in a search space of very high dimensionality. It's not trivial to come up with a sensible partitioning of the data. And because it's such a high dimensionality, an exhaustive search is out of the question. But you might think to yourself, well, maybe it's not that critical. Maybe we can just split the data up half and half and it'll be okay. Well, these initial set of naive scheduling results say otherwise. So the graph on the left, which is the same graph that I was referring to earlier, that's being run on a CPU, and we see that we can get 10 frames per second if we run the graph just using that device. If we move to using the GPU only, obviously the input data starts on the CPU, so that's why on the second graph we have red initially and then going to blue, which is the GPU that contains the display. Then we get quite a good performance improvement, 30 frames per second, so 3 times speed improvement, which is great. So if we thought to ourselves, well, let's just split each of the images up into a half or roughly a half and send half of it to the GPU and half of it to the CPU, well, what happens? And as you can see from the third graph from the left, it's not very good. And the reason it's not very good, well, there's a couple of reasons. The first reason is that a lot of time is spent transferring data to and fro in order to do the effects. And secondly, the faster device is often stalled, waiting for the slower device to finish. You can see that when we actually try to use 3 devices, 2 GPUs and a CPU, in the fourth graph, it's actually even worse. So this just kind of gives you a feel that the scheduling problem can't be solved by just thinking, I've got n devices, let's just split my pictures up into n pieces. So what to do? Well, as I mentioned earlier, just managing to do an effect well on a specific set of devices isn't enough. That local optimization, thinking that I can just solve a little piece of the graph problem, doesn't get you a nice global solution. We really do need a global optimization strategy. We need a way of sampling the search space in a guided fashion without becoming stuck in a local minima. And so what we decided, we did some research, and it became clear that there was an algorithm out there called the Metropolis-Hastings algorithm, which is a Markov chain Monte Carlo method, which was actually very good at sampling in a guided fashion these high dimensionality spaces and coming up with highly efficient, optimal solutions to these problems. And as I said earlier, what the input to this scheduler is the processing costs for each effect on each device, data transfer costs between devices, and data access patterns for all effects. Basically, you give the graph and that information to the system, and it will beaver away, and it will find you a very good schedule. A few notes on our systems that we've been building and the scheduler that we've come up with. The scheduler assumes that we have full availability of all devices. So, for instance, if the scheduler isn't told that halfway through the run you're going to start Chrome, then it probably won't give you a very good answer. It assumes that it has the resources that it thinks it has. The initial cost analysis of transfer and execution times can take many seconds. So the profiler will go through a set of routines whereby it transfers things between all of the devices, it runs the nodes on each of the devices for varying sizes of imagery, and it comes up with a deep understanding of each of the devices and the relationships between them. But when parameters change within the graph itself, let's say I want to change the radius of a blur, then that might mean that the apron size changes, and we can reschedule just a portion of the graph very quickly and come up with, we can reprofile a portion of the graph, and then we can reschedule very quickly, usually under a second. So it's not something that is, it's not that time consuming really. We cache schedules so that they can be reused if the same graph is encountered again. And actually, we're able to find, although the scheduler is really working on data parallelism, it is able to discover some task parallelism when, by overlapping the processing of one node with another. So this is what happens when you use the fully fledged Metropolis-Hastings scheduler on the graph that I showed you earlier. You've seen the first 2 graphs before. You've seen the GPU-only graph, which gives very good performance of 30 frames per second. And you've seen the second graph, what happens when you try to do it yourself. You find that it's not very easy, and the performance falls off a cliff. But the next two graphs are interesting. The next two graphs show what happens when Metropolis Hastings gets its hands on the graph. And you can see now that just by using a CPU and the GPU, we've managed to improve the frame rate to 35 frames per second. And when you add a second GPU, then the frame rate rockets to 45 frames per second. It's worth noting here that the scheduler is also aware of which GPU or which device is the display device, and it makes sure that the results at the end of the processing all end up on that device. So that's why, as you go through these graphs, they tend to become bluer, because it's the blue device that has the display. There's a few things here actually worth mentioning. One of them is that just because a device exists doesn't mean that the scheduler will decide to use it. As you can see in the second two graphs, the CPU wasn't really used that much. And in fact, on the last graph, apart from providing the input and transferring and actually running the schedule, it wasn't really used at all. And that's inevitable. Sometimes the transfer costs are just too great, and the performance of the CPU is just too low that the scheduler, in its infinite wisdom, decides not to use it. Okay, just some conclusions. We've created technology for exporting nuke effect graphs and efficiently running them across multiple devices in real time. The effect graphs are written once in Blink within nuke. The graphs are then exported to run in a suite of applications that we've written at the Foundry, providing the opportunity for real-time performance. But in order to really get that real-time performance, we needed to invent a sophisticated scheduler, which is based on the Metropolis Hastings stochastic sampling algorithm. And as I've shown in my previous slide, this can give rise to considerable speed improvements over naive scheduling. Further work, we want to focus on this transfer limitation. We need to look at better ways, better technologies of getting the data between the devices. For instance, there's lots of technologies out there for delivering live data straight to GPU memory, so we're going to look into those. Direct GPU to GPU transfers. At the moment, in order to get data from one GPU to another, it goes through CPU RAM, so that's not very efficient. And finally, in this section, asynchronous transfer and execute. And by that, I mean that at the moment, you transfer data to a device and then you process it. What would be cool is if you can transfer data to a device while you're doing a previous piece of work, effectively hiding a lot more the transfers to those devices. And we want to investigate explicit data parallelism, task parallelism. Any questions? And don't forget to come to see us on the booth.
Thank you, Bruce. Questions? All right, this one.
Thanks. I was wondering if you, what kind of parameters you're feeding to the graph. Are these like static performance metrics the devices have, or are you considering historical profiled empirical data from the past?
Yeah, it's empirical. At the moment, the data that's fed to the graph is the performance of the actual effects that are in the actual graph.
So
you might run them on small images just to get a feel for how well that device actually performs on that node.
Okay, so essentially you're starting out with a naive distribution. It falls off the cliff, and the scheduler then picks up or sees that it's performing bad and picks up the profiling data and then reschedules. We
could do that. I mean, in practice, what would probably happen, because in practice graphs are changing a lot in the work of the artist, then what will happen when, I mean, a lot of this work that I've spoken about today will end up back in Nuke. We've taken everything out of Nuke to give us a more researchy kind of environment to work on, but it will go back into Nuke. And as a consequence, as you know, in Nuke, graphs are manipulated and changed all the time. And so, yes, while they're being manipulated and changed, we can have a naive schedule. And then in the background, we can come up with much better schedules based upon empirical data and how those naive schedules were actually performing, the results from the different devices, etc.
Right. especially because many of the operations on the data would be, their performance would be data dependent.
There'll be
some tiles perform better than others and so on.
Yeah, I mean, and it is a hard problem. I mean, I'm not underestimating the fact that, yes, there will be some parameters will be well behaved. You know, if I change a blur radius, I can kind of predict what the outcome will be. But certainly within Blink, you can write algorithms that have conditional statements within them. And if those conditional statements were dependent upon input data, then they might perform quite differently. So I think the task of finding the best schedule is a very tough one. But I think that I feel really quite confident that we can find really good schedules that can evolve over time and get better and better as the graphs are being run. And we can get that empirical data, feed it back into the scheduler. And because the actual scheduling doesn't take that long, the initial profiling can take a long time for a big graph, many seconds, but the actual schedule itself, it's been written in a very good way. It's seriously multi-threaded. You can do that schedule in fractions of a second. So you can have that as a background task that can, when it's finished, it can then kick in and learn from its mistakes if it finds it makes mistakes.
All right, thank you.
You mentioned that it can take many seconds for the profiling to decide how to partition tasks.
Well, there's two things.
Devices.
The partitioning doesn't decide the profiling doesn't decide the partitioning. The profiling gives you the information that the scheduler can use to decide the partitioning.
And that takes how long when you say
It's under a second to do the schedule.
Okay.
It's many seconds to do the profiling.
But not minutes?
No.
Like 10, 5 seconds, something like that? Okay.
Yeah.
So I assume it's still, in order for a more complex graph than the one you were showcasing, to be prepared to operate in real time, you need a very skilled nuke operator that also knows his way around Blink and how to effectively maybe combine nodes to do something alike.
Yeah. I mean, one thing that we're considering is that for large graphs, I don't anticipate that there will be a global schedule for that entire graph. I think that we'll intelligently break the graph down into subgraphs and we'll schedule those. So that means that if someone makes a change to a piece of that large graph, it doesn't affect the schedule for everything. It also means that the scheduling can be done very fast for that little piece. When I say little piece, I might be talking about sort of, 50 nodes or something. But as we know in Nuke, you can have maybe thousands of nodes. So there may be lots of little schedules that are going on that are cached that can be brought in when they're seen to be reusable.
That's a good one. I wonder if this seems to be a standard problem. Did you look into any other? Is there no library on the market that does?
No, we've not found a library on the market. No. If there is one and we missed it, then. But yeah, we're not aware. I mean, there's obviously plenty of work that goes on, research work that goes on in this area, and it's certainly an area of active research. And we did have a good review of the literature, and we decided that the Metropolis Hastings was a good candidate, and so we tried it out, and we've had good results with it so far. It's very good. The Metropolis Hastings is very good at being able to find good solutions in as I said, high dimensionality space, high dimensional spaces that have lots of local minima, lots of spiky, noisy. Because the thing is with a scheduler is you can get just one thing wrong and the whole performance of the schedule falls off a cliff. So the space that's being searched is very, noisy is not the right word. I can't think of a better one, but it's not very C2 continuous, let's say.
Not linear.
Yes, it's not, it's complicated, yeah.
So a couple of things on the final schedule I thought quite interesting. So the jump in performance with a second GPU.
Oh, that's the wrong way. Oh, it's all gone
but
wrong.
what was that?
Well, that was in case anyone wanted to see a Blink kernel. I have one up my sleeve. But
Or was that the question we're supposed to ask?
No. Yeah, John, I've paid you a £5. Why are you asking that question? Yeah, let's go back to that.
So on the final schedule, so on that final schedule,
yes.
So you put a new GPU in your machine.
Yes.
I buy a new GPU.
Yes.
I've doubled the price on my GPUs, and I want my program to go twice as fast. Mm-hmm. So I'm interested in why it didn't go twice as fast, And also why there isn't a little slice of red everywhere.
Mm-hmm.
Is it not just fractionally faster to use those CPUs there? It's just interesting. Why did it not pop up?
I mean, I think that one of the interesting things is you're trying to kind of interpret the schedule results and try and figure out why it decided this schedule. An interesting point is that quite often what we've tried is to run a schedule overnight and do a really deep analysis of the space. And we find, actually, when you do that the results that we get after a second are near enough always pretty damn good. So we have quite a lot of confidence that these schedules that we're getting are the right schedule. It's not that they're highly suboptimal. So when I'm trying to answer your question about why is there no red, I think that the answer, because it's hard to know what the scheduler was thinking, if you like, it's because that the transfer rates of taking that data off the CPU and putting it onto the GPU for the next, because don't forget some of these are random access, right? So the bilateral filter, for instance, is random access. And that means data has to be shoveled around the place quite a lot. And if the CPU just doesn't have the performance characteristics, in general, I mean, it's really hard to say, but GPUs are often, they're not hundreds of times faster than are claimed, but they can well be 5 to 10, 20 times faster than CPUs. I think this is a 12-core Xeon that we used here, and that was up against 2 high-end GPUs. And so I think that the scheduler just deemed that it wasn't really useful. I think also the fact that the results have to end up on one device, on a GPU, because that's where the monitor is, puts a bit of weight towards doing things on the GPU as well.
I'm the engineer of the scheduler. I can add a speculation on why it's not using the CPU, if you'd like. Effectively, there's a constant overhead in kicking off any operation on the computer. Now, if these, again, this is only a speculation, as Mark says, we can't really know why the scheduler decided that this was the best point in the space of possible schedulings. But I imagine that if the CPU was allocated, say, 5 rows or 3 rows or some tiny part of the image, then there would be a constant overhead that is incurred for each of those executions. And the scheduler probably decided that making the portion 5 rows bigger on a GPU to avoid the constant overhead was a good idea. I would speculate that's probably why the results came out like this.
I think it's probably a mixture. I think that's a major factor, but I think that the extra transfers and the low performance of the CPU compared to the other GPUs, I think it all goes in that kind of mush of reasoning, if you can call it that the scheduler used.